48. Okay. In that case, we will go to our blue book page. Oh, it'll be somewhere near 27, maybe just a little bit past 27. Oh, no. We actually made it to 28 in this block. We're a little bit ahead of the other block, so we had made it through page 28. On page 29, there is one more example that should you want to go through it, we could. However, it's a lot like the other ones in that you will be given one of the things in an integrated rate, or you'll be asked for one of the things in the integrated rate law expression. You'll be given all of the others. Do we feel like we would like to go through that, or do we feel like we should just move on? Move on? Okay, excellent. So we are now done 1.6D, and we will move on to 1.6E, which is half-lives of reactions. Has anyone heard of half-lives before? 1, 2, 3, 4, 5, 6. Okay, like half of you. That's okay. If you haven't heard of it, the concept is really easy. It is the time it takes for the reactant concentration to decrease to 1/2. Shockingly, it's the half-life, the time it takes for it to decrease to 1/2 of its initial value, or to 1/2 of whatever time you started at. So if you start at 100%, a half-life would be the time it gets to 50%. And then another half-life would be the time it takes to get to 25%, and then 12.5% and 6 point whatever the heck it is percent. Yeah? And we can actually tell from the graph of A versus T, if we look at the lengths of the half-lives, we actually don't even need to, take the natural log if it's not a straight line, or take the 1/, take the reciprocal if it's not a straight line. You can actually tell from the length of the half-lives whether you have 0th order, whether you've got 1st order, or 2nd order. 0th order you should be able to tell anyway, just from A over T, because what do you get when you plot concentration of reactant versus time for 0th order? You get a straight line. Oh, there we go. All right, so there's our straight line. But what we can see from this is if we go from our initial concentration, which in this case is 0.2 molar. Okay, there's our first point there, 0.2 molar. Half of that is 0.1 molar. Okay, so we got 0.1 molar. And so that's our second point right there. And the time it takes to get from the first one to the second one is our first half-life. Okay, that's our first half-life. And that to me looks to be at about, if this is 30, then that is about, what, 33, 34, something like that. Okay, well, let's call it 34. All right, could be 33, but doesn't really matter. 34 seconds. Ish. Okay, maybe I should have put an approximate sign in front of that, but close enough. Our second half-life, is it as long as the first half-life? To go from 0.1 now to half of that, which is 0.05. So we're going from here to here. Is that the same amount of time? No, it is less. It is a smaller amount of time. We would expect it to be, I don't even know what we would expect it to be. Let's see, if that is 34 and that's at 50, then this would be about 16 seconds. Okay, And then our third half-life from 50 to 60 would be about 10 seconds. The actual numbers are unimportant, but what you can see is that in a 0th order, the half-life changes as time goes on. And it doesn't just change in any way, it gets smaller as time goes on. So for 0th order, half-life gets smaller. Now, if we plot first order, and again, we're not bothering to take the natural log. We've just got our concentration of A here, right? And we do A versus concentration of A versus time. The first half-life to go from 0.2 to 0.1 is, in this case, how many seconds would that be? That would be 5, 6, 7 seconds. And then our second half-life would be the time it takes to go from 7 seconds to 16 seconds. Did I do that right? No, 14 seconds. I can't do math. 7 to 4. Oh, guess what? That's also 7 seconds. And even without finding those numbers, if you look at the length of those half-life lines, are they the same or are they different? They are the same. So if you have first order, half-life is constant. Anyone want to guess what happens for second order to the length of the half-life as time goes on? It increases. It's the only thing left, right? And we can look down here and we can see that indeed for a second order reaction, you can see that the half-life is increasing. So this would give you another tool if you wanted to explain from a graph why you know a reaction is first order or second order or third order. You know, for 0th order, I think it would be enough to just say, oh, it was a straight line when we graphed A versus concentration of A versus T, so obviously that is 0th order. But for first order, you could say, hey, I've got a constant half-life. That indicates that I've got a first order reaction, right? If I graph A versus T and it's got a constant half-life, that is first order. And if you graph it and you're like, oh, okay, well, for second order, it increases. My half-life gets bigger for second order. So without doing any of the graphing, that's another way to argue your case for why a reaction is the order that it is. I guess for completion's sake, we should fill in this box over here. 0th order of A versus T shows that half-life does what with decreasing concentration? As concentration decreases, the half-life decreases. For first order, if we graph A versus T, as concentration decreases, what happens to half-life? Half-life stays the same. And for second order, what happens with decreasing concentration to the half-life? It increases. Okay. To be honest, though, I think AP doesn't care if you know the relation between half-life and the decreasing concentrations in the various orders. It's not that you can't use it, there are other ways to go about it. You can take the natural log, you can take the 1 over whatever, and if you forget them, it's not the end of the world, yeah? Because there's other ways of doing it. But what AP cares about is that you can deal with first order half-lives, and that's because they give you a formula related to first order half-lives on the data sheet, okay? So 3 things you need to know about first order. First one we already know for first order half-life is constant. Radioactive decay is always first order. So if they give you a radioactive isotope, like, have you guys heard of carbon-14 dating? Okay, that looks at the half-life of carbon-14, and it measures the amount that is in there, and it tells you how old something is because you can predict its half-life because the half-life is constant. And the formula that relates half-life, which we call T1 half, and the rate constant K is given in the AP data pages, and it is T1 half equals 0.693 over K. Let's go prove to ourselves that it is there. Oh, look, underneath our integrated rate laws, we have the half-life equation. First order half-life. Excuse me. Okay. So here's just an illustration, because it may be that you've never seen radioactive decay before. The graph. Basically what you can see is that we start with how much cobalt-60 is remaining at any given time. Cobalt-60 is a radioactive isotope. It could be written like this. Okay, so let's say we start with 10 grams of this cobalt-60 after one half-life. So here we have the percent of the cobalt remaining on the y-axis, and on the bottom, we've actually not even got it in time, we've got it in the number of half-lives, and we can do that because the half-life is constant, because this is radioactive decay, and radioactive decay is first order, okay? So after one half-life, we've gone down from 10 grams to 5 grams, which means we're now at 50%. In the next half-life, we've gone from 5 to 2.5, and so on down the curve, okay? And the half-life of cobalt-60 is 5.27 years. That means that T1 half is 5.27 years. So if they were to ask you how much remains after 15.81 years, you could be like, oh, 15.81 years, that sounds like a multiple of 5.27, right? And you'd be like, okay, 15, they'll normally give you nice numbers that are divisible. Like that, you'd be like, oh, that's 3 times. So that's 3 half-lives. So you go, oh, first half-life takes me down to 50%. Second half-life takes me down to 25%. Third half-life takes me down to 12.5%. So one way, if they give you lovely, nice numbers, you can just draw a little chart with all your half-lives, and you can say, after half-life number 1 has gone by, if we've got Na24, which has a T1 half equal to, whoa, that was crazy, 15 hours. And if we start with 64 grams, and I should put here that the mass is in grams, although that now looks like a gas, so I'm going to put grams down here. Could you guys fill in the rest of the chart? So they could ask you any of these questions. They could say, how much is remaining after 4 half-lives have passed? Or how much is remaining after 75 hours have passed? And that's, 75 is a nice round value into which 15 divides, right? So you could say after 75 hours, that's 5 half-lives. Just half it 5 times. Now, they're not always going to be lovely numbers that fit this pattern. Although, to be honest, multiple choice and stuff like that, they're going to be nice, easy ones like that. If it's not nice, easy numbers, you can use the half-life formula and the integrated rate law formula together. And because this is radioactive decay, what order is sorry, I've got a cough drop in my mouth. What order is radioactive decay? First order. So we're going to be using our natural log formula. Okay. So the half-life, here's our example, a half-life of a first order reaction, so we're first order, is 35 seconds. So T1 half is 35 seconds. Please calculate the rate constant. So all you're going to do is you're going to say, okay, this is a first order, so we can use this one because this is first order. They're not going to give you 0th order. They're not going to give you second order. They're going to give you first order because they've given you the equation. Solve for K and find it. So go ahead, do that. Did you in your work put your seconds down there? Good, because that tells you that your unit is seconds to the -1. Now, if we want to, our next thing is to calculate the time required. Yeah.
So, in that case, for A,
yeah,
sig figs be 3 or 2, or like.
We've got 35 seconds, so 2 sig figs.
But did you want to say like the person one is like the sig figs?
That's not a perfect number. Because how did you find 35 seconds? You had to measure it. Anytime you measure it, not a perfect number. Okay? Yeah. What's that? If they say exactly in the question, then it's a perfect number. Okay? Yeah. Then it's an exact number. But so 2 sig figs here. So we want the time required for part B for 95% of the sample to decay. Now, is our T1 half equals 0.693 over K going to be helpful here? No. We are told that 95% of the sample decays. Where should we go from there? We should use our integrated rate law. And if we look at our integrated rate law for this one, we have, well, we've got K already, right? We just solved for it. Yeah. We've got half-life. Yay. Or no, we don't have T. We don't have time because we're not looking at our half-life. We're asking for the time, the actual time, not the half-life time. Do we have concentration of A at time T, and do we have concentration of A at time 0? Yes. What is the concentration of A at time 0? 100%. Okay? So the concentration of A at time t is 100%. What is the concentration, or sorry, not times t, at time 0? Concentration of A at time t, how much is that? 5%. Now, because we're given these square brackets, what do those square brackets measure? What's the unit? Moles per liter. So let's not use percents. Let's use moles per liter. Okay. So we're going to say let, and this is important, or you could say assume, A at time 0 is equal to 1 molar. You could also say 10 molar, okay? It doesn't matter. You could say 100 molar, but that's weird. That's a weird concentration, yeah? But if it's 1 molar, then A at time t is equal to 0.05 molar. This here is important because is the actual concentration 1 molar? No. So if you're making an assumption, you have to say assume or let, okay? Now, you can solve the integrated rate law for t, or you can plug the numbers in and then solve for t, but in this case, I solve for t. Let's plug in all our numbers. But the one thing I want you to notice is that for the k value, even though my answer for k was 0.2, am I using the 0.2 or am I using my unrounded value? Use the unrounded value. Again, this is important. Why is it important? It can mess up, it cannot just mess up your sig figs, but it can give you like a rounding error. The worst case scenario, let's say you had 4 steps and you rounded off every time, right? What if you rounded up the first time and the second time it had to round up and the third time it had to round up and the fourth time it had to round up? You're going to end up with a value that is way, way too high. But it's just as easy to have, like, if this is your second step, for it to be out by a digit, okay? It won't always happen. Sometimes you'll get the right number with the rounded value, sometimes you won't, but it is better to always use the unrounded values and only round to the sig figs at the very end, okay? We chuck everything into our calculator and we get 151.3, but we have to remember that the actual number here had 2 sig figs, right? Even though we're using 3 digits, that number had 2 sig figs, so our answer should have 2 sig figs. Is good? It's occurring to me that if you're looking at a first order reaction, that you actually could just use percentages instead of molarities, because what happens to the unit when you take the natural log? Magic, it goes away, poof. Okay, so you could just, I think you could just use percentages there, but anyway, je ne sais pas. Example, the next example, this one, I think it's too straightforward to even worry about. The only thing to note we've got a rate constant. So that's our K value right there. And we're asked, what is the half-life? And the half-life is T1/2. And you go, oh my gosh. And this is a radioactive element. And so that tells us we can use that formula. You know K, you know 0.693, and you can just solve for T1/2. And the only thing to watch is to make sure that you have your unit in your work. Okay? Example number 4. Oh, okay. The radioactive isotope, copper-64, is used in the form of copper 2 acetate to study Wilson's disease. I imagine that none of that is relevant to this question. Ooh, here's some stuff that is, other than the fact it's radioactive, so that gives us first order. This isotope has a half-life, T1/2, is equal to 12.70 hours. What percent of copper-64 remains after 64 hours? Well, those aren't nice numbers. If I make a little table, that's not going to be beautiful, is it? So let's say I am going to use my integrated rate law. But in order to use my integrated rate law, which is the ln of concentration of A at time t minus ln, is it? It is, isn't it? Yeah, okay. I wanted to make sure I'm not doing it backwards. Ln of concentration of A at time 0 is equal to KT, and I think that's negative. Let's check. Where'd it go? Negative KT, it is. Okay, negative KT. In order to use this, I would need a K, right? How can I find a K? Use the half-life equation. Okay, so we throw our T1/2 in there, 12.70 hours. Boom, there we go. All right, and then you pick a concentration for your initial amount. And since we picked a concentration, we're going to say let, remember that's important, or assume. That A0 is 1 molar, or 100%. And that means that A at time t is what we don't know. And so let's solve this equation for ln of A at time t. So I've taken the negative ln of A0 and I moved it to the other side. And A0 we substituted in a 1. We substituted in K. We substituted in our 64 hours for time. You get that, and you get the ln of A is equal to negative 0.3492. Now, we don't want the natural log of A, we want regular concentration of A. Do you guys know how to do the inverse of natural log on your calculator? When in doubt, if you want the inverse of something, it's probably the second function or the shift. Okay, so what I'd like you to do is I would like you to, on your calculator, find your natural log button. And probably above your natural log button, it says e to the x. Okay, So it depends on your calculator whether you use second function or whether you use the shift button. And you'll get that. Because how do you do the opposite of a natural log? Natural log, you probably don't remember this from last day, but natural log is log base e. And e is some weird number. I forget what e is. 1 point something, 2 point something, something like that. Yeah. Okay? It's an irrational number. When numbers started becoming irrational and then imaginary, I got less excited with math. I was like, what is this business? I don't know. All right. All you need to know is that if you want to take the opposite of the natural log, it tells you what to do on your calculator, right? And so you're going to say, to find undo a natural log, I am going to take e to the negative 0.3492. Yes? So that's all you do, and Bob's your uncle. You get 0.03043 molar, which is, in other words, if we started with 1 molar, that is 3.04%. I think this one would have been better to do with just percentages than molarity, because then it would spit out a percent and you wouldn't have to convert your molarity to a percent. So I think you can just do it with percentages. Okay. Sometimes you can complete these types of problems without involving the rate law equation at all. Let's take a look at our data here. We have iodine 131, radiotherapy. Okay, so that's a radioisotope. Yeah. Sure, that sounds good. Probably. I'll go with that. What did you get?
No,
oh, okay. $2.718. That number sounds really familiar. 2.72, that is the value of E. Okay? Don't really worry about understanding it. Your math teachers will teach you about E. They'll teach you about natural logs. Okay? As long as you can punch the button, you're good for Chem 12 and good for AP Chem. All right. So we are told that it has a half-life of 8 days. T1/2 equals 8. What fraction of the dose will given to a patient will remain after 24 days after the treatment? So all for this one, all you would have to say is how many half-lives have passed? How many half-lives have passed? 3. So after 1 half-life, you have a half left. After 2 half-lives, you have a quarter left. And after 3 half-lives, you have an 1/8 left. That would probably be a multiple choice type question. Yeah? And you're like, okay, done. Boom. Didn't have to use any formulas or anything because the numbers were nice. 24 is a multiple of 8. Okay? Like I said, for multiple choice, they'll probably give you a multiple of 8 or a multiple of the half-life. All right, what else have we got? Oh, we can make a general rule for half-life reactions. I never remember this. So you can learn it, not learn it, whatever. The fraction of A remaining is 1/2 to the power of n. If you want to use this, you'll actually have to either understand it well enough that you can derive it on your own or remember it. So that is a choice that you will make should you want to, use this, okay? Because this one is not given on the data table. I don't think you're going to have to use it. I think they're going to give you nice numbers, but just in case, or if you go to university and you're like, oh my God, they're giving us all kinds of weird half-life stuff. I've still got those notes from Ms. Spence. I'll dig out where it says half-lives, right? You could do that. N is the number of half-lives. So we could try our copper 2 acetate question again. You remember how we had to use the T 1/2 equals 0.693 over whatever, and then use the integrated rate law, and that took a little while, right? You could just use this. Okay, so you're going to calculate how many half-lives have passed. And all you do for that, even though it's not going to be a nice number, you're going to say the time that has passed is 64 hours. And this is our half-life. So how many half-lives have gone by? 5.0394 half-lives have gone by. What fraction remains? It's just going to be 1/2 to the number of half-lives. Which is 0.034, which is what we got before. So 3.04% remains after 64 hours. It's a fairly straightforward formula, but like I said, I always forget it from year to year because it's usually 2 years in between me teaching it. I'm like, oh, I forgot about that. That's kind of cool. You should be able to read a graph and get information from the graph. What is the half-life of magnesium-28? How much remains after 50 hours and how much has decayed at 70 hours? And what is the rate constant for the decay of 28 mg? Try those questions there, please. Thank you. You can just put them on the counter if they're not. They fit? Okay, good. Okay, what's the half-life of magnesium-28? Everyone should have done that by now. The first one. Half-life is 20 hours. Excellent. Carry on. After 50 hours, how much Mg28 remains undecayed? 0.19-ish, okay? We have to ballpark it a little bit, right? We go up and across and we're like, oh, we're about here-ish. 0.19, 0.18, something like that. How much has decayed at 70 hours? %90. And what is the rate constant? Is good? Yeah. Not quite good. What have I done wrong? I need what? Is it 0.08? Did I do it wrong? Oh, okay, hang on. 0.693 divided by 20. No? Okay. So we're good with the number. Is there anything wrong with it though? Sig figs. Okay, so let's take that to, let's assume that that's 20 hours. Okay. And so that's going to be 0.035. And we need hours to the -1. There we go. Perfect. Yay. Yay. In the unlikely event, this is on our next page after the stars. In the unlikely event that AP decides to give you a 0th or second order half-life reaction, do not panic. Simply use the integrated rate law and set A at time t as the half-life. Set the time as the half-life and set the concentration of A at time t to half of A at time 0. Does that make sense? So you'd be like, okay, A at time 0, we are told that the initial concentration is 0.5 molar, and we are told that this is a second order reaction, so we're going to be using this one here. And we are given the rate constant here. And we are told that A naught is equal to 0.50. Yes? And we're going to say that our time is the half-life. Okay, so that means that our concentration is going to be half of what it once was. And then you just chuck everything into the integrated rate law formula. Blah, 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 blah. You've got concentrations, you've got a rate constant, solve for T. Hooray, and you get 250 seconds. Is good? They're never going to ask you that. I can't imagine them doing it. You would do the same thing for 0th order. There's some exercises there. We're not going to get to those today. Your homework is to complete the review as best you can, because remember, your last chance to ask questions is tomorrow. Somebody in my first period asked me what suggestions I have for studying. Number 1, obviously do these. Number 2, you have a vocab list, right? That I gave you at the beginning of the year. If you have lost it, let me know. I do have extras. Okay, it would be good to go through that and see, do I know all these terms? They all have pictures that go along with them. The other thing that would be good to look at would be your what's on the test. Yes, if you've lost that, let me know, because I also have copies of that. And you can go and be like, oh, can I do, point 1A? Can I do B1? Can I do B2? Whatever it is. All right. You can study with Buddy if you want to. I never find that was very effective for me, unless I really didn't know what I was doing, in which case it was nice to have phone a friend as an option. Yeah.
Can you show me where the bulk of this is up?
Ah, yes. I think it's just in the regular file for that unit. Let's take a look. General files. Unit 1. Let's make sure it's here. Reaction kinetics terminology. I'll rename that to Unit 1 vocab, hey? There we go. Now it looks more official, rather than whatever random name my file had in my own filing system at home. 2018.